Hello, class. Before we start today's lesson, I thought we would just kind of discuss again where we are. We finished 2325 yesterday. So we can cross that out. Thought it deserved a little fanfare. And today we're going to do lesson on 2627. So that's where we're going to start today. If you can print the handout, that would save you an awful lot of writing today. Otherwise, you can take notes in your notebook. So section 2627 is honestly a little more important than what we did yesterday with the synthetic division. So that's why I'm going to leave 2325 behind and get into rational functions so we can spend a little more time there. So this is a topic you learned last year. It's chapter 9 in the Algebra 2 book. And to start, an informal definition of a rational function. It's when you have a polynomial over a polynomial and it can't be reduced. And that's informal because there's nothing technical here. And I should remind you the denominator, of course, can't be 0 because if the denominator is 0, then the whole thing's undefined. But you're going to know that you have an equation of a rational function when you have a polynomial over a polynomial and it doesn't reduce. Okay? So, for example, look at function j. That's a linear over linear. That's a polynomial over a polynomial. Look at function f. It's degree 2 over degree 1. It's a polynomial over a polynomial. And all of these so far have two terms. So look at function g. This is a rational function because 5 is a polynomial. It's degree 0. When you have just a constant, that's degree 0. So that's a constant polynomial over this quadratic trinomial. Quadratic because it's degree 2, trinomial for 3 terms. And then this is also a rational function because we have a polynomial over a polynomial. And none of these can be reduced. Nothing I'm going to show you in the next couple of days can be reduced, so I won't try to fool you on that at this point in time. And when you look at the graphs of rational functions, now that we've looked at the equations a little bit, if we look at the graphs of rational functions, what I want you to notice are the asymptotes. That's what rational functions are really well known for. They can have horizontal asymptotes. They can have vertical asymptotes. The asymptotes guide the function at the extremes. So this function is going to go out forever, approaching that asymptote, coming from above, approaching that asymptote forever, but not crossing it at the extreme. This is called a branch. These two pieces are called branches. And this branch approaches the horizontal asymptote from underneath. So this one approaches from above, this one approaches from below, and out at the extremes, it's going to get closer and closer and closer, but not cross it. And similarly with the vertical asymptote. You can also have slant asymptotes. You may or may not have seen slant asymptotes in Algebra 2. Some of the teachers show it. I do not when I teach Algebra 2. I save that for Precalc. So that's called a slant or oblique asymptote. The word oblique just means a line that's not horizontal or vertical. So a slanted line is an oblique line. And here's some other. This one has a horizontal asymptote over the x-axis. It's a little hard to see, and it has these vertical asymptotes. And this one has a slant asymptote. So looking at these 4 examples, and just 4 examples to kind of get started with, I have some questions I'd like to ask. So just based on these 4 examples, can you look at those and first tell me, can a rational function have more than one vertical asymptote? Yes, this one right here, function g, has 2 vertical asymptotes. So as it turns out, rational functions can have, they can have 1, they can have 2, they can have none like this one. And we could even make them with 3, 4, 5 vertical asymptotes. We probably won't see any like that. But for vertical asymptotes, it could be 0, it could be 1, it could be 2, it could be even more. Next question. Does every rational function have an x-intercept? No. Not every rational function has to have an x-intercept. So this one has an x-intercept because it crosses the x-axis. This one looks like it has 2 x-intercepts, but this one doesn't have any x-intercepts. So never does this graph touch the x-axis. So a rational function does not have to have an x-intercept. And one more question. Can a function cross its own asymptote? Yes. And that one might be a surprise. Because when you first start learning asymptotes, when you first start learning them, you learn them for exponential functions, right? And for exponential functions, when you're in Algebra 1, you learn that that never ever touches the asymptote. But that's true for exponential functions, but that's not true for every single function that has an asymptote. If you look down here at function h, this graph actually crosses that slant asymptote right there at the origin. So graphs can sometimes cross an asymptote, and it's a little bit surprising, but if it happens, it'll happen somewhere near the middle. It won't happen necessarily at the origin. It could happen a little left or a little right from that. But the asymptote is still used by the function. So if you look at this graph, see how it kind of crosses and bumps back down? As we go out to the right up here, the graph comes back toward that asymptote, and it will get closer and closer and closer to the asymptote as we go on forever. And out here, it won't cross at the extremes. I don't know if you heard me say that before, but when I was talking about the asymptotes up here, I mentioned at the extremes. So a graph actually can cross an asymptote if it happens somewhere near the middle, but it will not happen way out to the right or way out to the left. Okay. Next thing in the notes is to be able to determine some major characteristics of rational functions. So in order to find major characteristics, here's kind of your guideline. And if you were able to print that out, you save yourself a lot of writing. If you are not going to print that out, you do want to pause the video and make a note of these important ways to find major characteristics of rational functions. And instead of reading all of them to you right now, we'll look at domain, y-intercept, and x-intercept as we do examples. Vertical asymptotes we'll look at as we do examples. And then just to note for horizontal and slant, because that's kind of the newest part. To determine if your rational function will have a horizontal or slant asymptote, you have to compare the degree of the numerator to the degree of the denominator. And when you compare the degree of the numerator to the degree of the denominator, there's really only a few things that can happen. If the degree of the numerator is smaller than the degree of the denominator, automatic horizontal asymptote y equals 0, nothing else to think about. If the degree of the top is equal to the degree of the bottom, then there's a horizontal asymptote, and here's how you find it, and I'll show you an example of that in a moment. Now, if there's a slant asymptote, that only happens when the degree of the top is bigger than the degree of the bottom by exactly 1. So a couple things to note here. Often I get asked, what if the degree of the top is bigger than the degree of the bottom by more than 1? So what if, for example, you have like a degree 5 over a degree 2? Well, then it's not this, it's not this, and it's not this. So you have neither horizontal nor slant asymptote. Another question that often comes up is, can a rational function have a horizontal and a slant asymptote? No, a rational function cannot. There might be functions out there in the world that have a horizontal and a slant asymptote, but rational functions will not have both. And that's because these are mutually exclusive. Mutually exclusive means they can't happen at the same time. If the degree of the bottom is smaller than the degree of the top, degree of the top is smaller than the degree of the bottom, then the degree of the top can't be bigger than the degree of the bottom. It's impossible for these things to happen at once. It's impossible for these two things to happen at once. And it's impossible for these two things to happen at once. So you're either going to have this kind of horizontal asymptote, or this kind of horizontal asymptote, or this slant asymptote, or none of them. And we'll see that as we do some examples. So let's jump into our first example. We are going to do these instructions for that example. And so let's begin by finding the domain. For the domain, the notes say that it's going to be all real numbers except the zeros of the denominator. So we're going to take the denominator and set it equal to 0. That right there is the only thing you can't have. And we actually know this from our work earlier in the year. So the domain for this function is going to be all real numbers in the entire world except -1. And that should make perfect sense, because if you look at this, if you go to plug in -1, what happens in the denominator? You get 0. So you get, if you plug in -1, the top becomes -1, but the bottom becomes 0, and that's undefined. So we know that we can't have 0 for the denominator. So that's how you find the domain. Now, when I find the domain, I like to, right at that point, find the locations of any vertical asymptotes. And the reason is, if you look at the notes for vertical asymptotes, to find where they are, you set the denominator equal to 0 and solve. So check that out. We just did that. So we set the denominator equal to 0 and solve. The resulting real zeros are vertical asymptotes. So since the only real 0 here is x equals -1, that is the one and only vertical asymptote. So I usually find those together because you find them using the same procedure. By the way, if you have any imaginary zeros, then they don't count as vertical asymptotes. We're not going to see that today, but I'll make sure you see that tomorrow or next lesson. All right, so we got the domain. We got a vertical asymptote. Let's continue with the asymptotes. Let's see if we have a horizontal or a slant asymptote. So to figure that out, we need to compare the degree of the top to the degree of the bottom. So if we look at this rational function, the top is degree 1 and the bottom is degree 1. The degree is the highest power of x in each polynomial. So the highest power of x in the top is 1, and the highest power of x in the bottom is 1 as well. So this scenario, the degree of the numerator is equal to the degree of the denominator. So what that tells us is there's going to be a horizontal asymptote at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. The leading coefficient of the numerator is 2. The leading coefficient of the denominator is 1. So we have a horizontal asymptote at y equals 2. And those are the asymptotes, because if the degree of the top is equal to the degree of the bottom, then this one's certainly not going to happen, and neither is this one. So when it comes to horizontal and slant asymptotes, you're looking for one or the other. You're not looking for both. And now we want to find intercepts. So if we look back at the notes, we'll see some information we should be well aware of, because to find a y-intercept, we always set x equal to 0 and solve. And to find an x-intercept, we always set y equal to 0 and solve. This is how it works no matter what kind of function you're working with. So let's go ahead and look for a y-intercept. So to find a y-intercept, we're going to set x equal to 0. 2 times 0 is 0, so the numerator becomes 1. And in the denominator, when I put 0 in for x, I get 1. So my y-intercept is 0, 1. It does say coordinates, so make sure you don't just put y equals 1. Go ahead and put 0, 1 for that ordered pair, please. And then for the x-intercepts, we're going to set y equal to 0 and solve. Now what happens when you set y equal to 0 and you go to solve this is you have a rational equation. So to solve, we would multiply both sides by x plus 1. What happens on the left-hand side is you have 0 times that, so it's still 0. On the right-hand side, these reduce because that x plus 1 would be like an x plus 1 over 1. And we get 0 equals 2x plus 1. So we're going to have x equals negative 1/2 when we solve. So this particular example has one y-intercept and one x-intercept. And just to note, a potential shortcut for you if you do notice this. When you go to find the x-intercepts, when you set y equal to 0, what's going to happen every single time with a rational function is when you multiply both the denominator on both sides, every single time it's going to reduce here, and the left-hand side will stay 0, or the right-hand side, wherever the 0 is. And what happens is you get the numerator equal to 0. So as a shortcut, if you want, there's no need to do this, but as a shortcut for finding x-intercepts, if you want, you can just set the numerator equal to 0 and solve. Because what's going to happen in every single problem is when you multiply both sides by the denominator, it's going to cancel out anyway, and you're going to be left with the numerator equals 0. So at this point, we have found all of our major characteristics. And before I take out that calculator, I want us to think about what we found and see if we can possibly make some predictions. So let's get a little sketch going. Let's go ahead and set up some axes, a y-axis and an x-axis. There's a vertical asymptote at -1. And there's a horizontal asymptote at y equals 2. There's a y-intercept at 0, 1. And there's an x-intercept at -1/2, 0. So that's kind of what I know about this graph so far. And even though we've only seen a few examples this year, and you only learned this for the first time last year, I bet when you look at this, you can start to make predictions or guesses as to how many branches this graph will have. Do you think this graph will have 0, 1, 2, 3 branches? How many? I'm guessing 2. There's probably a branch down here like this, right? That's my guess. We'll find out in a minute when we graph it on the calculator. And I might be right, I might be wrong. I'm just trying to predict based on the examples I've seen in the past. And then for that second branch, could it be above? Could it be here? No, because then you'd fail the vertical line test. So for that second branch, it's either going to be on a diagonal in this corner here, or it could be side by side. A lot of times you'll find that we end up on diagonals, but they actually can be side by side, the branches. That would pass the vertical line test, so that's no issue. So this particular one is going to end up with the second branch on that diagonal there. And I only know that because I have done this example before. Otherwise, you would really just be taking a guess at this stage. So to graph this in your calculator, when you go to graph it in your calculator, you have to make sure that you put parentheses around the numerator because it's two terms before you hit divide, and put parentheses around the denominator. So when you have a rational function, you have to make sure you're using parentheses properly when you put it in the calculator. So here's number 1. I have my other ones lined up already, but you see the equal sign is turned off. They're deselected, so they're not going to show up on the graph. So when I hit graph and I'm in Zoom Standard, this is the picture we get. And it looks pretty good compared to what I had set up. So let me draw in that other branch. If we wanted to be more accurate with this branch, we could pick X's and find Y's, but I'm guessing nobody wants to do that. I don't particularly want to do that either. We do have these calculators, so we might as well use them. And if you wanted to, you could graph the horizontal asymptote so you can see it. It's y equals 2, and you can see it guiding the function. The function approaches it from above in this branch, and this branch approaches it from below. The calculator doesn't have like a really easy way to graph a vertical line, so you're not really going to be able to graph the vertical asymptote because the calculator is programmed to only graph functions. And if you think of a vertical line, it's not a function. So that's why the calculator doesn't allow you to do that, because you can't put it in the form y equals. So just so you know, there is a way to technically do it, but I don't usually cover that. It's not something I utilize anyway. So this looks good. And that's our first example. I think we're ready to move on to number 2. So here's number 2. We're going to do all the same instructions for f of x. And we can find those things in any order we want, but let's go ahead and jump in and find the domain first. To find the domain is going to be all real numbers except the zeros of the denominator. So we set the denominator equal to 0. This factors pretty nicely. So please don't use the quadratic formula on that one. And we actually end up with 2 restrictions here. So the domain is all real numbers except the zeros of the denominator. So the domain is all real numbers except -1 and 2. And that's what that looks like in interval notation. If right now this was a little bit of a leap for you, if you forget how to put this information into interval notation, the key to that was a number line. So if you set up a number line, you can remind yourself that you want these 3 intervals, because your domain is any real number in the entire world as long as it's not -1 and as long as it's not 2, because those are the 2 numbers that if you were to plug in, the bottom would become 0. And we don't want 0 in a denominator, because then that would be undefined. So that's my domain. When I find the domain, I always like to immediately find the vertical asymptotes, because the vertical asymptotes are found by setting the denominator equal to 0, which we just did. And any real zeros are vertical asymptotes. So what that means is our vertical asymptotes, we have 2 this time. We have x equals 2 and x equals -1. You could write those in the other order, but we have 2 vertical asymptotes this time. Let's go ahead and see if we have a horizontal or a slant asymptote. To determine if there's a horizontal or a slant asymptote, we need to compare the degree of the top to the degree of the bottom. So the degree of the numerator is 1. The degree of the denominator is 2. So this scenario is the degree of the top is smaller than the degree of the bottom. So that means there's automatically a horizontal asymptote at y equals 0, and there's no work to do for that one. So we got the domain, the asymptotes. Now let's find some intercepts. if there are any. There don't have to be. So I hope you don't mind that I keep bringing back the other page of notes. If you have it printed, you can just look at your other page. But for anyone who didn't get a chance to print it, I thought this might help. So let's go ahead and find the y-intercept if there is one. So for y-intercept, we're going to set x equal to 0. And when we do that, we're going to get 0 up top. We have 0 minus 0 minus 2, and that comes out to 0. So the y-intercept is 0, 0, and that's the origin. So in this case, the y-intercept is actually also an x-intercept. And we'll discuss that a little further in just a moment. Now, when we go to find x-intercepts, we set y equal to 0. And when we set y equal to 0, our next step is to multiply both sides of by the denominator. So if you recall the shortcut from the last example, you can save yourself a little bit of writing. Because what's going to happen every time here is this times 0 is still 0. And this is going to reduce out because we're multiplying by what's down in the denominator anyway. So now we've solved. We have x equals 0. Since we set y equals 0, that gives us 0, 0. If you do get the origin as an x-intercept or a y-intercept, you don't have to write it twice like I did here. You could just label that it's a y-intercept and it's an x-intercept. I just figured going through the instructions step by step, it might be easiest for us if I just labeled that as y-intercept and write it again for x-intercept. And that's the information we have so far. So once again, let's plan this graph before we see it on the graphing calculator. Because the more of these you see, the better you get at predicting what they look like. So we have a vertical asymptote at x equals 2. We have a vertical asymptote at x equals -1. We have a horizontal asymptote along the x-axis, y equals 0. It's a little hard to show, so what I do is I usually make it a little darker. If you have a different color, that might be helpful. And you can also extend it out further than the x-axis itself, and sometimes that helps if there is an asymptote that overlaps the x-axis, it helps you see it better. And then the only intercept I have is 0, 0. So I actually don't have any other information about this graph. But just based on the examples you've seen, maybe you can take a guess. How many branches, how many different pieces do you think this will have? I think it's going to have 3. So I'm not sure if there's going to be a piece up here or down here. I'm not sure if there's going to be a piece up here or down here. I'm not sure yet. You could take a guess. You can't have both, though. You can't have this and this because you fail a vertical line test. And then for that piece in the middle, there's a few different options. The piece in the middle sometimes will go like this. Or sometimes it'll go like this instead. Or it could be like a U or kind of like a bent, crooked U. We really don't know. So I do think there are going to be 3 pieces here. And the more of these you see, the better guesses you can take. And if we didn't have a graphing calculator, we could certainly make a table and plug in x's and find y's. That's actually what we do in Algebra 2. So my Algebra 2 students this year, they had to make a table and find some extra points to figure out where the branches went. But since this is review for us, when I do this in Precalc, I just let us graph it on the calculator to find out. The numerator is only one term, so it doesn't actually need parentheses in the calculator. It's okay to put them. But the denominator must have parentheses when you go to graph this in the calculator. And I did not turn that back on. So let me hit enter on the equal sign. And now that's selected and it will graph. And here are the 3 pieces that we expected. Okay, so I have one piece here being guided by this horizontal and this vertical asymptote. Notice for this piece, this vertical asymptote has nothing to do with it. So for this branch, this vertical asymptote has nothing to do with it. That's okay. It's still guided by this horizontal and this vertical asymptote. The piece in the middle, that's actually not what I expected. I thought it was going to go up like that. But it comes down like this, almost like a kind of like a flip of a cubic function. And it is bound by asymptotes. It approaches this vertical asymptote up to the left. It approaches this vertical asymptote down to the right. But it actually crosses right through the horizontal asymptote. So this branch doesn't use the horizontal asymptote, and that's okay. Just like, remember this branch didn't use this vertical asymptote. That's okay. They don't have to use all of them. And then that third branch uses this vertical asymptote and the horizontal asymptote. And that's the sketch of our graph. I have one more example for us to see today. And that's number 3. So for number 3, same instructions as the previous ones. So to find the domain, we're going to set the denominator equal to 0 and solve. And any real zeros have to be excluded from the domain. So the domain is all real numbers except 3. And once again, that should really make sense because we know that from our work back in chapter 1 earlier in the year. When you have a fraction, the denominator can't be 0 because you'd be undefined. And by the way, I've been putting a comma here. If anyone wants to use the union symbol, feel free. Either way is fine with me. When you find the domain, you also find the locations of any vertical asymptotes because the vertical asymptotes are where the denominator is 0. Any real zeros are going to be vertical asymptotes. So this graph is going to have one vertical asymptote. And then here's what I think is the interesting part for this one. The degree of the top is 2. The degree of the denominator is 1. So degree 2 over degree 1. That's this scenario right here. The degree of the top is bigger than the degree of the bottom by exactly 1. So there's going to be a slant asymptote. In that slant asymptote, to find out the equation of it, we perform the division. So a lot of people look at that and say, what are you talking about? What division? Well, look at the function itself. It is a division problem. It's a numerator over denominator. This is your dividend. This is your divisor. So what you're going to do is do this actual division, and the equation of the slant asymptote will be y equals the quotient, and we'll ignore the remainder. So for this particular problem, you could do synthetic or long division. I tend to do long division on all of these when I'm doing slant asymptotes. I think the reason is a lot of times you get like a degree 3 over degree 2. So if this were degree 2, you'd be forced to do long division. So I'm kind of just used to doing it. And these are usually quick ones. So when you have a slant asymptote, usually the division is going to be pretty quick anyway. So I don't mind doing the long division. But you could do synthetic if you want for this one. So what do we multiply by x to match x squared? X times x is x squared. And x times negative 3 is minus 3x. And then we have to remember to subtract that line. So to change both signs, I get 2x plus 0. And then what do I multiply by x to match 2x? Plus 2. And then this is negative 6. Remember to subtract that line. And the remainder comes up to 6. But the good news on this, if you ever make a mistake on just the remainder part, it doesn't matter because it said we ignore the remainder. The equation of the slant asymptote is y equals the quotient. Y equals the quotient. So it's y equals x plus 2, and that's the equation of your slant asymptote. Make sure you don't just put x plus 2, because x plus 2 on its own is not a line, but y equals x plus 2 is a line. I'm kind of excited to graph this, but we have to finish finding the other important characteristics, the y-intercept and x-intercept. So for the y-intercept, we're going to put 0 in for x. The top will become 0. The bottom becomes negative 3. So once again, we get 0, 0. This graph is going to pass through the origin. So that'll be an x-intercept as well. But be careful. In the last example, this was the y-intercept and it was the only x-intercept. Don't assume that always happens. Actually take the time to try and find the x-intercepts, because when you set y equal to 0 for this one, you're actually going to get 2 answers. So if you assumed this was the only x-intercept, you'd miss out on the other one. So if you want to do this the full way, you set the entire thing equal to 0 and you multiply both sides by the denominator. If you'd like to just take a shortcut and set the numerator equal to 0, you're welcome to do that. And then to solve this, we'll factor out an x. We get x equals 0 and we get x equals 1. So one of our x-intercepts is 0, 0 as we expected, and the other is 1, 0. So this one actually has 2 x-intercepts instead of just 1. So one more time today, let's set up our graph and plan ahead. We have a slant asymptote at y equals x plus 2. That's just a line in y equals mx plus b form. So we have a y-intercept at 2, and then we have a slope of 1. So we're going to go from 2, we're going to go up 1, right 1, up 1, right 1. We can also go down 1, left 1. And that's our slant asymptote. We have a vertical asymptote at x equals 3. And then we also have a y-intercept at 0, 0. And we have an x-intercept at 1, 0. So taking a look at this, it looks like there's going to be a branch here. And then I think there's going to be a second branch. I'm just not sure if it's going to be up here in this part or over here in this part. So to find out, let's graph on our calculator. Remember to put parentheses around the numerator and parentheses around the denominator. And when I go ahead and graph that, I get the piece down here that we expected. And then there's a little tiny blip up here that you might not even notice. However, because we planned out the graph, we probably assumed there were going to be 2 branches here. I have to erase a little bit. I planned poorly, so I'm going to go ahead and erase this part just to have some extra space. And unfortunately, I used some pen there, so white out as well. Okay, so what we have in this graph is we have a piece down here that approaches the slant asymptote. It goes up just a little bit over the x-axis, and then it's going to come down and use the vertical asymptote. My graph is by no means perfect, but I'm doing the best I can with the information I have and the sketch that I have. And then to see what's going on up here, what I'm going to do is go into my window and just increase my Y max. I want to see up a little bit higher. So maybe 15, I'm going to make it 20, see how it looks. And then we can see that there is indeed another piece up here. And that other piece up here goes like this. Right now, the dimensions look different. It looks like wider or larger than the piece here, but that's just because the viewing windows are different. And if you want to put in that slant asymptote, you can. So if I go in here and put y equals x plus 2, the calculator will graph that slant asymptote for me. And then you can see that the graph really is bound by that. So this piece down here, this branch on the lower left, approaches the slant asymptote from underneath, and the piece up here approaches from above. And if you can visualize a vertical asymptote in there at y equals 3, you can see that the 2 branches are bound by that as well. So that is your introductory lesson to rational functions. And we'll do a little bit more lesson tomorrow and some practice. Thanks for watching, guys. Have a good day.